Okay, so welcome to the course here. So we will be talking about geometric structures on two orbifolds. First, we will be the review of manifolds and differentiable structures. So these are the some basic informations, and so first we'll have some we'll review on manifolds and differentiable structures, and basic thing will be we'll review manifolds and discrete group actions and separation manifolds and surfaces. So this will be our topic this week, and in the second on Thursday we'll do pseudo group and G structures. We'll discuss G manifolds and examples. And we also discussed differentiable geometry and the relation to G structures. And so these will just be basic reviews. Some people might not be so familiar with this fundamental bundle, principal bundles and connections and flat connections. So this is my course homepage, and some preliminary knowledge should be something like algebraic topology, chapter 01. So this is just on the fundamental group and covering space theory, and maybe some differentiable manifold theory, and maybe this book is very old, but this is still a very good book, and maybe some Riemannian geometry would be helpful, and Kobayashi and Nomizu's book on the foundations of differentiable geometry. So this is a very good book, but of course he deals more with connections here instead of Riemannian geometry, and so that's more general than these connection theories are more general than the Riemannian manifold theory. And finally, this is a very old book, Geometry of Manifolds. It also deals with lots of connection theory, and it's maybe more intuitive than Kobayashi and Nomizu. So another really good reference is the Thurston's lecture notes. This is you can download it from here. This book is not really written yet. It's just a preliminary copy, but I think that but it has really good ideas, and you can get lots of inspiration from this book. So this is a three-dimensional geometry and topology. So this is actually published version of this book, but of course this contains a lot more than what is here, and it is a good reference for our course as well. And so if you want really further generalization of differential geometry, you can go to this Cartan's generalization, and it is a full generalization of differentiable manifold theory and Riemannian manifolds. So for example, this book by Ivy and Landsberg, explains this theory quite well. And we will also use this book by Braden on compact transformation groups here. And Berger 1, so Berger Geometry 1, this is written for French teachers in France in 1980s. It does have lots of beautiful geometric theorems, and it is very rigorous. So I recommend this book. And of course, I mentioned that Kobayashi and Nomizu's Foundations of Differential Geometry. So this is in Springer. So to begin with manifolds and differentiable structures, so we do mostly some review, and it's going to be intuitive account. So following theory for manifolds will be transferred to orbifolds. We will briefly mention them here as a review, and this theory will be generalized to orbifold later. We mostly follow the corner-free approach to differential geometry, and we do not need to really compute curvatures and so on. So these will be G structures covering spaces and remaining manifolds with constant curvature, Lie groups and Lie group actions, and principal bundles and connections. So these will be our mostly topics, how we will approach this subject. So for topological spaces, I'm not going to define anything, but you should recall what quotient topology was and so on. That will be very helpful. And we will mostly use cell complexes. So this is in Hatch's part, page 5 to 7. We will only consider some finite cell complexes for convenience. And given topological spaces, we can do lots of constructions like products, quotients, suspensions, and joins, and so on. So please review these kind of things. So I'm not going to really go through these things. So manifolds. So topological N manifold is, or just N manifold, is a Hausdorff space with countable bases, and the chart is to Euclidean space. En. So for example, curves and surfaces and 3 manifolds are these examples. So charts could also go to a positive half space Hn, then the set of points mapping to our this boundary on the chart is well defined and is said to be the boundary of the manifold. Of course, we need the invariance of domain theorem to say that the boundary is a well defined set. Okay. So Rn, Hn themselves are, of course, is topological N manifold, and open subsets of Rn or Hn are actually topological N manifold. Sn, so unit sphere is again a manifold. So here you need some sort of a stereographic projection to cover Sn by Euclidean neighborhoods to show that it is a manifold. So another example is Rpn. Here it's actually quotient of Sn by order 2 group, and you can show these also a manifold. Or another way to see it is a manifold is to use an affine patches. So affine patch means some set of points which where it satisfies some linear inequality. And n-ball is a manifold with the boundary. So if you take a unit n-ball, then it's again a manifold. The boundary is the unit sphere. Given two manifolds m1 and m2 of dimension m and n, then the product is again a manifold of dimension m plus n. And so annulus is a disk with the interior of a removed with the interior of a smaller disk, and so then it becomes a manifold with two boundary components, and it's also homeomorphic to circle times cross interval. So n-dimensional torus is defined as some product of n circles. Okay, so if you look at something like two torus, then there's a various way to realize these two torus, but of course they are all homeomorphic. So another way to look at the n torus is that consider Tn to be the group of translation generated by this translation by standard vectors, in standard direction. Then Rn mod Tn is again homeomorphic to this Tn. So again, you're using quotient topology, which I'm not explaining here. And the connected sum of two n manifolds m1 and m2. So you remove the interior of two crossbar from mi for each I. Then the so you remove one crossbar from each mi, and then each mi has a boundary now component homeomorphic Sn minus 1. Then you identify the spheres. Okay, so then the result is again an n manifold. Okay. So of course we need to prove that by saying that the neighborhoods identified to some neighborhoods and so on. So take, for example, two-dimensional tori and projective planes and do connected sums. So then you can obtain all the compact surfaces in this way. Okay? So I mean up to homeomorphism, of course. So let's recall some homotopy theory. So let X and Y be topological spaces. Homotopy is some map from X times I to Y, and so maps F G are homotopic if F is fx0 and Gx is fx1 for all X. Then so given X and Y, you say they're homotopic if this is true. So the homotopy property is actually an equivalence relation. You can verify that, and of course homotopy equivalences of two spaces is a map from F going to X and Y and the map G going from Y to X, so that F circle G and G circle F are homotopic to identity X and identity Y. So this is a sort of a way to reduce study of topological space up to homotopy, and hopefully that might, in the hope that it will be simpler. So let's recall what the fundamental group is. So a path is a map from F I going to X. So I is really here interval from 0 to 1. Linear homotopy. So for any two paths in Rn, there's a linear homotopy. So the Rn has no interesting group, this sort of thing. So homotopy classes, equivalence classes of homotopy relative to endpoints. So here you need the homotopy relative to n. So that means that so this homotopy map has to be constant on the endpoint times the identity. So that's a little bit different than just general homotopy. So fundamental group is actually the set of homotopy classes or passes with endpoints just x0. And so then the product exists by joining these or what you call concatenation. Then the product gives us a group. Okay, so that's called the fundamental group. And the change of base points gives us an isomorphism, but this is not a canonical isomorphism. So you can have 2 points, and this pass will give you pass between the base point will give you isomorphism. So if you have different paths, which is not homotopic, then the isomorphism might be different. So that's not. So it's not canonical isomorphism. So fundamental group of circle is Z, or it's infinite cyclic. So then the broad fixed point theorem follows from this fact here. And of course, if you have any map F from X to Y, that sending X0 to Y0, then there is an induced homomorphism from fundamental group to fundamental group. So this is a very useful fact, more powerful than what you think of.